Welcome to this comprehensive scientific lecture on the fascinating science behind freezing sushi to eliminate pathogens and parasites. Today we'll explore how precise temperature control and time protocols can make raw fish safe for consumption by destroying dangerous parasites and bacteria. Let's begin by understanding what biological threats exist in raw fish that require freezing treatment. Raw fish, particularly marine species, can harbor dangerous parasites, such as Anisakis simplex, which are nematode worms that can cause severe gastrointestinal illness in humans. Additionally, bacterial pathogens like Vibrio species and Listeria monocytogenes pose significant health risks, especially in immunocompromised individuals. Here's a simplified representation of an Anisakis larva, a parasitic nematode commonly found in marine fish. These organisms can survive in the human digestive tract and cause painful infections. You might ask, how common is Anisakis infection in populations that consume raw fish? Research indicates that some fish species, particularly those from colder waters, can have up to 90% prevalence of Anisakis larvae in their tissues. Now let's examine the fundamental thermodynamic principles that govern the freezing process and pathogen destruction. The energy required for phase transition is given by Q equals mass times the latent heat of fusion. For water, the latent heat of fusion is approximately 334 kilojoules per kilogram, representing the energy needed to convert ice to water at 0 degrees Celsius. That's 334 kilojoules per kilogram, or 334,000 joules per kilogram. This graph shows a typical temperature profile during fish freezing. Notice the plateau at the freezing point where latent heat is being removed. Understanding ice crystal formation at the cellular level is crucial for both safety and quality. During freezing, ice crystals form both inside cells, intracellularly, and outside cells, extracellularly, with different implications for tissue structure. The critical radius for ice crystal nucleation is given by this equation, where gamma is surface tension, Tm is melting temperature, ρ is density, Lf is latent heat, and delta T is supercooling. With slow freezing, large ice crystals form that can damage cellular structures and reduce fish quality. Fast freezing creates many small ice crystals that cause less structural damage and better preserve texture. You might wonder, what freezing rate best preserves fish quality while ensuring safety? Research shows that freezing rates of 1 to 5 centimeters per hour through the thermal center of the fish create optimal small crystal formation. The FDA has established specific temperature and time requirements for parasite destruction in fish intended for raw consumption. Option 1. Maintain at minus 20 degrees Celsius or below for 168 hours, which is 7 days. Option 2. Maintain at minus 35 degrees Celsius or below for 15 hours minimum. These two protocols are equivalent in terms of parasite destruction. The colder temperature allows for much shorter processing time. Interestingly, the European Union has different requirements, mandating minus 20 degrees Celsius for only 24 hours minimum, showing variation in international safety standards. The rate of pathogen and parasite destruction follows Arrhenius kinetics, allowing us to predict kill rates at different temperatures. The Arrhenius equation states that the rate constant K equals the pre-exponential factor A times e to the negative activation energy over R times temperature. For parasite destruction, the activation energy typically ranges from 50 to 100 kilojoules per mole. Taking the natural logarithm of both sides gives us a linear relationship between log K and 1 over temperature. This linearized form shows ln(K) equals ln(A) minus activation energy over R times 1 over T. This Arrhenius plot shows how the destruction rate constant decreases exponentially as temperature decreases, requiring longer exposure times at warmer freezing temperatures. Let's work through a numerical example to calculate the required freezing time for a specific scenario. Consider a salmon fillet that is 3 centimeters thick being frozen in a commercial freezer maintained at minus 25 degrees Celsius. The decimal reduction time d equals the natural log of initial population over final population divided by the rate constant K. We want a 6-log reduction in Anisakis viability, meaning we reduce the parasite population by a factor of 1 million. The natural log of 10 to the 6th power equals 6 times 2.303, which equals 13.82. The required time equals 13.82 divided by the rate constant at minus 25 degrees Celsius. Using experimentally determined rate constants for Anisakis at minus 25 degrees, we get approximately 48 to 72 hours required exposure time. Notice this falls between the FDA's two extreme protocols, which makes sense given minus 25 degrees is between minus 20 and minus 35 degrees. Understanding heat transfer is essential for predicting how quickly fish reaches safe temperatures throughout its volume. The rate of heat transfer Q equals the convective heat transfer coefficient H times surface area A times temperature difference. For air freezing, the convective heat transfer coefficient typically ranges from 10 to 30 watts per square meter Kelvin. Inside the fish tissue, heat conduction follows Fourier's law, which governs how temperature propagates through the material. The heat equation states that the time derivative of temperature equals the thermal diffusivity alpha times the Laplacian of temperature. For fish tissue, the thermal diffusivity is approximately 1.4 times 10 to the minus 7 square meters per second. Heat must transfer from the cold air through the surface and then conduct to the center. The center takes longest to reach target temperature. Measuring and ensuring proper core temperature is absolutely critical for food safety compliance. The fish surface reaches the target freezing temperature much faster than the thermal core, creating a temperature gradient through the tissue. A simplified estimate for core freezing time is approximately the square of the characteristic length divided by 4 times thermal diffusivity. For a 3 centimeter thick fillet, the characteristic length to the center is 1.5 centimeters. Plugging in values, we get approximately 400 seconds, or about 7 minutes, just to reach thermal equilibrium at the core. Important: this is only the time to reach thermal equilibrium. The pathogen destruction time must be added on top of this. You might ask, why not just freeze at minus 80 degrees Celsius for much faster pathogen destruction? Answer: extremely rapid freezing at minus 80 degrees can cause quality degradation, including protein denaturation and excessive moisture loss during thawing. Water activity plays a crucial role in both microbial survival and tissue damage during freezing. Water activity is defined as the ratio of vapor pressure P to the vapor pressure of pure water P0. Freezing reduces water activity by converting liquid water to ice crystals, making less water available for microbial metabolism. Water activity below 0.6 inhibits most bacterial growth, though this doesn't directly kill existing pathogens or parasites. Water activity decreases progressively as more water is converted to ice during the freezing process. Natural salts and sugars in fish tissue act as cryoprotectants, lowering the freezing point and protecting cellular structures. The freezing point depression equals the cryoscopic constant times the molal concentration of solutes. Different parasites have different thermal death kinetics that influence freezing requirements. Anisakis simplex is one of the most cold-tolerant marine parasites, which is why FDA regulations are designed around destroying this organism. At minus 20 degrees Celsius, the decimal reduction time for Anisakis is approximately 24 to 48 hours. Diphyllobothrium latum, a tapeworm found in freshwater fish, is less cold-tolerant and dies more quickly during freezing. This graph compares the thermal death curves for Anisakis versus tapeworm parasites, showing Anisakis requires colder temperatures for equivalent kill rates. Let's examine the energy requirements for commercial-scale sushi freezing operations. Consider a commercial operation freezing 1,000 kilograms of tuna from 5 degrees Celsius down to minus 35 degrees Celsius. First, we calculate sensible heat removal. Q1 equals mass times specific heat times temperature change. From 5 degrees to freezing point at minus 2 degrees, 1,000 times 3.5 times 7 equals 24, 500 kilojoules. Next, latent heat for phase change. Q2 equals mass times latent heat times water fraction. For 70% water content, 1,000 times 334 times 0.7 equals 233, 800 kilojoules. Finally, cooling from minus 2 to minus 35 to 1,000 times 1.8 times 33 equals 59, 400 kilojoules. Total energy, 24.5 plus 233.8 plus 59.4 equals 317.7 megajoules required to freeze this batch. With a typical coefficient of performance of 1.5 for commercial freezers, the actual electrical energy input would be about twice this amount. Beyond safety, freezing protocols significantly impact the quality attributes of the final product. Drip loss occurs during thawing, when damaged cell membranes release intracellular fluid, reducing yield and quality. Drip loss percentage equals initial mass minus mass after thawing, divided by initial mass times 100%. Typical drip loss values range from 2 to 5% for fast freezing methods versus 8 to 15% for slow conventional freezing. This chart shows relative quality retention, with fresh fish as baseline, fast freezing preserving most quality, slow freezing causing moderate loss, and poor handling causing severe degradation. A common question: does freezing affect the nutritional content of fish? Answer: properly executed freezing has minimal impact on proteins, fats, and most vitamins. Some B vitamins may show slight reduction during extended frozen storage. Ultra-low temperature freezing represents the cutting edge of preservation technology. Ultra-low temperature freezing at -80 degrees Celsius or below is used for high-value products like premium bluefin tuna. Pathogen destruction time is proportional to E to the activation energy over RT, making ultra-low temperatures extremely efficient. At -80 degrees Celsius, complete pathogen destruction can occur in under 1 hour, compared to 7 days at -20 degrees. Compare the required exposure times at different temperatures: 168 hours at -20, 15 hours at -35, and less than 1 hour at -80 degrees Celsius. Liquid nitrogen at -196 degrees Celsius enables essentially instantaneous surface freezing, creating the smallest possible ice crystals. Successful implementation requires proper equipment, monitoring, and documentation systems. Regulatory compliance requires continuous temperature monitoring with automatic data logging throughout the entire freezing cycle. Multiple temperature probes must monitor both surface temperature and thermal center to ensure complete treatment. Temperature probes must be properly positioned, with the core probe at the thermal center and surface probes monitoring exterior temperatures. HACCP plans, which stands for Hazard Analysis and Critical Control Points, must include freezing as a critical control point with defined limits and corrective actions. Emerging technologies promise to improve both the safety and quality of frozen sushi products. High-pressure freezing combines extreme pressure, up to 200 megapascals, with cold temperatures to create uniform ice crystal formation. Electromagnetic freezing uses oscillating magnetic or electric fields to control ice nucleation, potentially reducing crystal size further. Electromagnetic fields can be used to control the formation of ice crystals during freezing. This concludes our comprehensive exploration of sushi freezing science. From biological threats to advanced technologies, we've covered the fundamentals of safe and quality-driven sushi production.